Right, CPU. There are loads of different ways of designing CPUs, but the one that we look at GCSE is von Neumann, which I can never spell. I think it's double M or double N. Okay, von Neumann. This is the concept of a CPU that stores instructions and data in the same memory. So if we just do a little block diagram, here's the CPU, and it's connected to our RAM and ROM, our primary storage. It's connected through a data bus and an address bus. The data bus is where the data travels to and from the CPU and the memory. The address bus is a selection system. Okay? The address bus is connected to one of the registers of the CPU. Can I remember? Yeah.
Memory address register.
Clues in the name, isn't it? Yeah. MAR. Whatever value is in the MAR, so if I've got, I don't know, 1000 in the MAR, that means we are going to access memory location 1000. That's all the memory address register does. When we read data from memory, it comes along the data bus. That sounds like a train, not a bus, but there you go. And it arrives at one of the other registers. Go on, Greg. Yeah, the memory data register. So the registers that have got memory at the start, there's two of them. One's connected to the address bus for selecting. One's connected to the address bus for storing data. But if you look at the way I've drawn the two buses, the address bus is one way because it's just instructing memory. The data bus is two way. Why is it two way?
Because there could be inputs and the store.
Yeah. So the CPU could say, right, oh, I've worked this thing out, I need to now store it back in memory somewhere. So yeah, I need to be able to write to memory. Right, so the MDR just temporarily holds things. There are two components of the CPU. You have the control unit. That is the thing that performs the fetch execute cycle. It is governed by something called a clock, which is what when we say 1.6 gigahertz, if I was doing this back in, when I did A-level in 1980, we'd be saying 1.5 megahertz. All right, so the clock speeds have sped up quite a bit in the last 30 odd years. Okay, so we're talking gigahertz, not megahertz. But the clock is the governor. Okay, it determines how quickly the control unit performs the fetch execute cycle, which is why, at a really basic level, if we increase the clock speed, we increase the general performance of the CPU. It's not strictly true, but in general that would be the case. Something running at 3.2 gigahertz, you would expect it to be executing faster than 1.6 gigahertz. All right? So the clock, the fetch execute cycle, that is all the control unit does. It performs the fetch execute cycle. It is probably the most boring job in the computer. Okay, so if anybody ever asks you, we're doing some like hybrid experiment, we're trying to merge computers and people together, would you like to be a control unit? Walk away. You do not want that job. Right, the fetch execute cycle. There is not much to it. We have the fetch part. That's where we fetch the instruction from main memory. It starts from the program counter. What is the it's the only register out of these ones that doesn't have the word register at the end. But it is a register. The program counter, what's the purpose of it? Yeah?
You can't have any program.
No? Right. Registers are storage. They just store something. So they represent a piece of data. They don't do any action. So the program counter holds a number which tells us what? Yes, Greg?
It needs to be connected.
Nope. Yeah?
When can we want to the next instruction?
Nope. Right. The program counter holds an address. That's all it does. It holds a memory location. The program counter's purpose is to hold the memory location of the next instruction to execute. When we turn the computer on, the program counter will have the value of 0. Now, memory address 0 doesn't actually represent RAM, it's a location in ROM. So that when we turn the computer on, the control unit goes, right, oh, fetch execute cycle, that's what I'm doing today. Okay, and he goes, right, okay, where am I getting my instruction from? And he goes, right, I know there's a register that does that. And it goes, right, it's the program counter. It tells me where the next instruction is located that I want to execute. So it copies that value to the memory address register. And then it goes, right, okay, so I have selected memory address 0. And it goes, right, okay, let's fetch the instruction. So that instruction goes, hey, sound like a train again, across to the MDR. And it'll just appear in the MDR. Once we've got that, so we need to copy the program counter to the memory address register. That's the first step of the fetch. Then we get the data, so we do a read. From that location. What we then do, that arrives at the MDR. Now, it is actually more complicated than this. But this is how we keep it simple at GCSE. So we then decode what's in the memory data register. Now, there is one really fundamental thing that we have to do. If I leave the program counter with 0 in it, what's going to happen when I do the fetch execute cycle again? Yeah, I'm going to do the same thing. So what we have to do, increment the PC. Okay? As soon as I've incremented the PC, what I then do, assuming I worked out what the instruction was, I execute the instruction. And then we go around it all again. Billions of times a second. Okay? Now, in general, programs are in sequence. Remember the constructs when we're programming. Sequence, selection, iteration. They go in sequence, so incrementing the PC is a good idea. You might get an instruction that says, oh no, we need to go off and do something somewhere else. So there are instructions which we call branch instructions, which will modify the program counter. Okay? So that we can go and do a function, subroutine. We can make a decision and do different bits of code. So there will be instructions that modify the program counter to say, right, don't do the next one, do the one down here. Do the instruction down here. So you've got these. There is one other component of the CPU.
ALU.
Yeah, ALU, quite an important one. And it's got the register inside it.
Our final name is ACC.
Yeah, accumulator. ACC. Is what we shorten it for because nobody wants to write the word accumulator. Right, accumulator. Just a temporary calculation register where it just stores things when we're doing some arithmetic. Because the arithmetic and logic unit handles all the adding, subtracting, all the math stuff, but it also handles not, and, or. It also handles comparing things. So when we write something in a high-level language like that, that's basically a comparison. So that's the job of the arithmetic and logic unit. But it also does things like shifts. So you know we talked about shifts like multiplying and dividing, all done by the ALU. Okay? All governed by that clock. Now there was a question, and it does keep coming up, about you've got two different CPUs, one with 2 cores and one with 4 cores. Okay? Right, let's just talk briefly about what that means. 2 cores means you've got 2 of these. Okay? 2 control units, 2 sets of registers. 2 sets of you're leaning on that. 2 sets of registers. Okay? Separate CPUs. That's what we mean by core. If you've got 2 cores, then you can have 2 fetch execute cycles running at the same time, which means you can execute 2 instructions literally at the same time. If you've got 4 cores, you can do 4. Now, automatically, you would think that this would be quicker, but that's not strictly speaking true. In order to take advantage of more than one CPU, you need tasks that can be split. So if you think about some of the algorithms we've done this year, so you've done merge sort and you've done bubble sort. If you think about bubble sort, you have to compare one pair at a time. And it's like, you go all the way through the list, and then you start again. So actually, you can only really use one CPU for that task, because it's a linear task. But merge sort, once you've done that initial split, and you start merging pairs of lists together, they're independent of each other, aren't they? So when you do that, you go, oh, we'll do this one, and then we'll move on and do the next pair, and then the next pair, and then the next pair. Well, actually, you could do all 4 of those merges at the same time without affecting each other. So if you've got a task that can be split, then you can take advantage of multiple cores. Some of the most powerful computers on the planet have 2 million cores. They wouldn't be able to run a bubble sort any quicker than my mobile phone. But give them 1 trillion pieces of data to sort, they could run the merge sort a bit quicker than my phone, because they could spread that load across all those CPUs. So when you're talking about taking advantage of multiple cores, you've got to think about the task. Is the task, can it be split up so that we can do separate parts of the task at the same time? If we can take advantage of more cores. If we can't, it's going to make no difference. The other thing that you often get, because of heat, generating heat, these might have a higher clock speed. So if these are running slower, and you've got a task that can't be use more than one processor at once, this is going to be quicker, because you're not using the other processors. When we got the first generation of true multi-core consoles, the Xbox 360 and the PlayStation 3, the initial games that came out were pants, because people couldn't make use of all the CPU power. Okay, on the Xbox 360 there was 6, because it uses hyperthreading. There were 3 cores but 6 execution units, so there was 6 instructions you can execute at the same time. But game engines were designed to work on 1 CPU. So you had like loads of CPUs like, know what to do, know what to do. But eventually people started to get their heads around this. So if you look at the initial PlayStation 3 games that come out, they were terrible. That was a really complicated architecture, the PS3. But when you see the games that Naughty Dog did, the Uncharted games, they were like epically better than the first PlayStation 3, because they were using all the CPU cores. They organised all their code in such a way that it could work to take advantage of the processing power that's there. So just throwing multiple cores at, I had a student years ago, he had a server at home that had 16 cores. And he had, and this is quite a few years ago, 24 gig of RAM. And I said, what are you doing with that? And he was just playing games on it. So I don't know where he got this thing from, but he was wasting his money. He had all this RAM and he couldn't use it. Don't know why he did it. Well, there you go. Right, so you've got to be careful when it comes to the old multi-core. But please, when you're talking about the registers, they just store stuff. They don't do anything. They are used by the control unit to hold data that it's interested in. That's what their purpose is. Okay? Obviously, they've all got a specific purpose. Program counter holds the next instruction's address. Memory address register holds the address we want to access. Memory data register holds the data that we've read or the data that we want to write back to memory. Accumulator is just like a temporary scratch area. Okay? Right, I'll start that one.